We are Team Smashville, made up of Chris Brown, Jonathan Seachek, and Kevin Elmlinger, and we are presenting Eyeglasses.
Okay, so first we're going to talk about how the eye works before we actually get into the eyeglasses topic. So first thing first, the cornea refracts the light that's coming in to pass through your pupil and into your iris, and the pupil can change its size to control the amount of light that's actually entering to prevent damage to your eye, so that if there's too much light, it can kind of close up so that it doesn't damage your eye, and then if there's not a whole lot of light, it can open up more so that you can actually see things better. And the retina then captures that light and relays the information to your brain and tells your brain what it is that you're actually seeing and allows you to see the things in front of you. And the lens and the cornea also allow the eye to focus that light more clearly so that it's actually a clear image instead of just a bunch of blurry lights. Moving on to the history of eyeglasses. The Romans first discovered that glass could actually magnify things in front of them so they could see through pieces of glass that things on the other side were actually bigger than what they would normally be. And 13th century Venetians were actually able to take this and make it into a handheld magnifying glass, and they were the first ones to do so. And then moving on from there, Italian monks created the first set of wearable reading glasses in around the 1280s. At the time, they could only do reading glasses and didn't know how to do further away because they could only use glass to magnify right in front of them. And Salvino Diamarte is often credited with being the first person to invent these wearable reading glasses. And then, of course, Benjamin Franklin invented the bifocals to be able to see both near and far in the same set of glasses, so you could look higher up on the glasses to see further away, or lower on the glasses in the bottom half to see things close up in front of you.
Alright, so I'm going to be talking about how the lenses actually work. So people who need corrective lenses either have myopia, which is nearsightedness, or hyperopia, farsightedness, and some have astigmatism, which essentially means that everything is blurry to you. People with myopia need to see far away, so the lenses that they use are called minus lens. The minus lens is concave, so the light diverges, creating a smaller size of the image. But the concave lens is meant to correct the focal point and make it longer because the focal point without the minus lens is too short and the image comes into focus before it reaches the retina. So with hyperopia, which is the opposite of it, they need to see up close. So they use the plus lens, and the plus lens is convex. So the light converges and increases the size of an image, and it corrects the focal point as the focal point is behind the retina. So it doesn't come into, so the image doesn't come into focus quickly enough for the retina. So it corrects that by making the focal point shorter. So that's it. So it is in line with retina. In astigmatism, everything is blurry, so they need to use a cylindrical lens, and the lens focuses the light into a line instead of a singular point, so that it creates a single focal point instead of two.
Okay, so here's the math for nearsightedness. To find the power of a spectacle lens or a corrective lens, you you need to use the equation. Usually, need to use the equation. Power is equal to 1 over the object distance plus 1 over the image distance. In this case, we'll be talking about a problem in which the far point is 30 centimeters away, and the lens is 1.5 centimeters away from the eye because of the eyeglass frames. If you want them to be able to see distant objects clearly, then you'd need to produce an image that's 30 centimeters away from the eye. That would mean that we would know, because of the eyeglasses being held 1.5 centimeters away, you'd subtract that from 30 centimeters and you'd get that it'd be 28.5 centimeters. If you look at the image to the left, that kind of shows it a little bit more, how on the top you would have to kind of look through the image and the distance object being on the like same side of the lens. Whew. And so to start the equation, we know that 28.5 centimeters would be negative because it's on the same side of the spectacle, and that the object distance would be approximately infinity because we don't necessarily know where the object is. And if we go down to the problem where it says under, as written earlier, we'd see that plugging in the values, you'd have 1 over infinity plus 1 over negative 0.285 meters. We'd put it in meters because it makes it easier to turn it into diopters. And since we could also assume that 1 over infinity would equal 0, just to make the problem easier for us, we would find that the power is equal to negative 3.51 diopters because you would subtract 0 from 3.51. And we know that this is correct because, once again, it's negative, and for nearsighted people, you would have negative diopters because it's the distance object and the image would be on the same side. So, moving on to math for farsightedness, it's a lot of the same thing, but positive. So, if we wanted to find the power of a spectacle lens or corrective lens whose near point is 1 meter, for a person to be able to see 25 centimeters away, once again, assuming that the corrective lens is 1.5 meters away from the eye, we would have to see that when an object is held to 25.0 centimeters away from a person's eyes, the spectacle lens would produce an image 1 meter away. So, assuming that the image distance is negative 98.5 centimeters, once again being negative because it's on the same side of the spectacle as the object. We could also assume that the object distance is 23.5 centimeters away because of subtracting the 1.5 centimeters of the eyeglasses. And when we move down to the problem, it would be to that formula, sorry, it would be P equals, or power equals 1 over the object distance plus 1 over the image distance again, which plugging in the values would get you 1 over 0.235 meters plus 1 over negative 0.985 meters. And transforming those into diopters would get you 4.26 diopters minus 1.02 diopters equals 3.24 diopters. This would be positive because, oh, sorry. This would be positive because the person is farsighted, and it's kind of the opposite when it comes to farsighted and nearsightedness. Farsighted people would have the thickest part of the lens be on the center, making it so that the power that's prescribed has to be positive. All right, and that's it for the presentation.